Okay, so we're going to go over our fourth and final example. So in this example, we have rather mundane. We have a dryer vent, not unlike what you might have in your house. So to dry your clothes, and you see the clothes all tumbling around and around and around. And what comes out of the dryer is mainly hot air and of course steam or like water vapor. And so we have air going out, and we're going to approximate the dryer vent length as 20 feet, and the diameter equals 4 inches. Okay, and there's some volumetric flow rate Q leaving it, and according to the manufacturer, of the dryer / vent assembly, L max of the dryer vent is 20 feet, and so there can only be 20 feet of pipe or a vent, which is a circular cross section, and there can only be 4 90-degree elbows. Okay, and this here is galvanized iron. So we might as well look on table 8.1, because you can bet we're going to need the surface roughness, so we might as well just get it while it is on our mind. And so galvanized iron, epsilon equals 0.000 3 zeros and 5 feet. Okay, and what's driving the flow is the pressure in the dryer, and so P equals 0.2 inches of H2O. Okay, and so the pressure in the dryer is not specified in the normal way, and this is a closed dryer. And so what's driving the flow out the duct is a pressure of 0.2 inches of H2O. And according to the manufacturer, if the dryer vent is too long, greater than 20 feet, and there is more than 4 90-degree elbows, the flow rate, the airflow rate leaving the vent will be too low, and you might damage the dryer. Okay, and then the last thing is that the temperature, because it is a dryer, the temperature equals 100 degrees Fahrenheit as it leaves the duct. Okay, and so our solution is at this maximum, in this worst case condition, find Q. Q at worst case condition, where L equals 20 feet and there are 4 90-degree elbows. Okay. And so we're going to assume, as always, steady flow, incompressible flow, and constant rho. Okay, and so this isn't too debilitating of a constant, because you would intuitively expect the high temperature air to actually cool down as it leaves the dryer vent, but it's actually not going to cool down that much to where it's going to affect the flow too much. Okay, and so the solution and Q equals pi over 4 d squared U average. Okay, and so the name of the game for this problem is we need to find U average. Okay, and we don't know that. We just know that there is a pressure of 0.2 inches of H2O in the dryer that's driving the flow outside. Okay, and in reality that comes from some sort of fan, but we'll just say that the pressure in the dryer is what's driving it. Okay, and so and we will assume that the A inside of the dryer is very large, which implies that U AVG in the dryer is small, and you can neglect that. Okay, and that's the same sort of tank argument that the velocity in the dryer is very small compared to the velocity in the duct, which means we don't need to account for the kinetic energy in the dryer. Okay, and that's the same argument that we have been making. So I'm going to call this here inside the dryer state 1, which is the inlet, and state 2 at the exit is the outlet. Okay, and we're also going to, and based on that, we're also going to assume that the air exits as a free jet. Okay, so we're going to use the energy equation like we always had. So that means P over rho G plus alpha U averaged squared over 2G plus Z at the outlet minus P over rho G plus alpha U averaged squared over 2G plus Z at the inlet equals W dot in over M dot G minus W dot out, which could be from a turbine, divided by M dot G minus the total head losses. Okay, and so we are approximating the element driving the flow not from a pump or a fan of some sort, so but from pressure, so there's no work into it, there's no turbine work out. We definitely are going to have head losses, so we need to include those. And we can also cross off Z. We're going to assume that the change of elevation is negligible. I mean, this is air, so you normally don't need to account for changes of elevation unless you're dealing with planetary length scales. And at the outlet, which is the exit of the duct, the air exits as a free jet. So we're going to assume that that's 0 because PATM, we're going to just take that to be 0. Okay? And at the inlet, U average squared is 0. So U squared is less than is very small in the dryer. So that goes away. Okay? And so we have most of the terms crossed out. And so we have alpha times the average velocity in the vent squared over 2G, which U averaged is again what we are after for this problem. So we can find Q, minus the pressure in the dryer, divided by rho G of the air, equals minus the head losses. Okay, so now we need to go and analyze this equation here, and we'll assume turbulent for the purpose of analysis, which means alpha equals 1, and check RED after the fact to make sure. Okay, and so if you do a homework problem and you don't know RED, so you don't know whether the flow is laminar or turbulent, after you do the calculation, assuming it is either laminar or turbulent, check the Reynolds number to make sure that your assumption is correct. If you don't do that, I will take off points on your quizzes and homework and final exam and things like that. Okay, that's just good practices. You need to verify your assumptions that they are correct. Okay, so now we need to find the various properties. Okay, so first we need to convert P of the dryer from inches of H2O to pound force per foot squared. Okay, and so how we do that is P equals rho, in this case, H2O G times H. So essentially, when a problem says that the pressure equals H length units of a fluid, that basically means that you have a manometer reading. So say we have the dryer here. I'll draw this a little bit differently. We have the duct, going out, and you could imagine that attached to the side of the dryer is a manometer. Okay, and that manometer is filled with water, and the height of the differential height of manometer fluid sorry, I hit that button again. Fluid is H. And so when they say that the pressure is 0.2 inches of water, that means that the differential height of a manometer that is attached to the side of the device, that it's filled with water, and the differential reading is 0.2 inches. So that means that you use the manometer formula to convert the pressure and height times the gravity times the density of the manometer fluid, which is in this case water. Okay, and so this equals gamma H2O times H, and so that equals 62.4 pound force per cubic foot times H, which is 0.2 inches. I should use the actual IN here, times 1 foot per 12 inches. And so this means that the pressure in the dryer, in terms of normal units, which we needed to convert from 0.2 inches of H2O, is equal to 1.04 pound force per square foot. So it's a very, very low pressure. P, just recall that P ATM in absolute units is equal to 14.7 psia, and that's equal to 2,106 or 2,116.8 pound force per foot squared, and P dryer minus PATM in absolute units. If you convert the dryer to absolute pressure, divided by PATM equals 0.049%. So essentially, the pressure of the dryer is essentially not much higher, is just very small and barely above atmospheric pressure. Okay, and so this is barely PATM in absolute pressure. Okay, so this implies that we can just use the standard pressure to evaluate. Okay, so if you had a very long duct to where the pressure was very high in the beginning of it, and you had air flowing through it, and it was long enough to have a significant pressure drop, it is very likely that the flow would be compressible to begin with, and the equations that we are going through here are no longer valid. Okay, and so here we're going to assume that if we're in terms of calculating the density of the air, that the pressure and the temperature are essentially constant. Okay, and so then from table A.7 at 100 degrees Fahrenheit, a rho equals of the air is equal to 0.00221 slugs per foot cubed. Mu equals 3.96 times 10 to the minus 7 pound force second per foot squared, and the kinematic viscosity is equal to 1.79 times 10 to the minus 4 feet squared per second. And I'll just make a note, mu is a function of temperature only. Okay, so even if you were to account for a small pressure change, that would not change the density. So because the density, or the viscosity is only a function of temperature, and also delta P is very small, so the delta rho due to P is also small. Okay, and so we can only use table A7 because the pressure is essentially atmospheric pressure. It's just a little bit above it, just enough to drive a tiny flow. If the pressure was high enough in the dryer, to where you needed to use the ideal gas law to get very accurate results, then your dryer would likely blow up, and it would be a very bad day in your house, because there'd be, at the very least, there would be clothes everywhere, and you would have to go to Lowe's or Home Depot to buy a new dryer, which no one likes doing. Okay, so now we have the properties. So we know P dryer. We are looking for the average velocity. Now we need to find the head loss. Okay, so now determine the head loss. So the head loss is equal to the head loss based on major losses, which are just friction from the pipe on the walls due to the fluid flow, and the minor head losses, which are due to losses due to the components and things like that. And so the major losses are the sum of the Darcy friction factor times L over D times the average velocity squared over 2G. Okay? And then also, the minor losses are the sum of all the components of their loss coefficient times the average velocity squared over 2G. Okay? And then, since we have a constant area duct, we can just simplify this to the U averaged squared over 2G times the sum of KL. Okay, and so for this here we have 4 90-degree elbows with KL equal to 1.5. That's from table whatever it is, 8.3. Let me look. Let me look what table that's from. That's from table 8.4. Okay, and also there is one sharp inlet. Okay, which is the dryer. So I forgot to write that down, but we're going to approximate that as a sharp inlet, and that sharp inlet has a KL of 0.5. Okay. And you can find that on table 8.2. Okay, and so the sums of the K's, this equals 4 times 1.5, because there are 4 elbows, plus 0.5, and so that's equals 6.5, is the sum of all the loss coefficients. Okay, so now we know that L equals 20 feet, and D equals 4 inches, which equals 0.333 feet. So we know L over D. We don't know the average velocity squared. We don't know that. And we don't know F, so we need to find F. So the total head loss is equal to F times 20 feet over 0.333 feet times the average velocity squared over 2g plus 6.5, which is the sum of all the loss coefficients, times u averaged squared over 2g. Okay, and then F, we're going to assume it's turbulent and check after the fact. So we'll just use the Colebrook equation again, as we always have. So that's 1 over square root of F equals minus 2 log base 10 of the relative roughness divided by 3.7 plus 2.51 over the Reynolds number based on diameter times the square root of F. Okay, and the relative roughness, epsilon over D, equals 0.0005 feet divided by 0.333 feet, because the diameter is 4 inches, which is 1/3 of a foot. That equals 0.0015. Okay, and so that is the relative roughness of the tube. And RED, that equals rho, U averaged, times D over mu. Or you can write the same thing as U averaged times D over the kinematic viscosity. And so the Reynolds number is equal to the average velocity, which we don't know, times 0.333 feet over 1.79 times 10 to the minus 4 feet squared per second for the kinematic viscosity. And the Reynolds number based on diameter, go back, that the Reynolds number based on diameter is equal to 1860 seconds over feet times U averaged. Okay, so then we stick everything in. We know epsilon over D, we know the 3.7, we got the 2.51, and then we got the number on the Reynolds number. So I'm just going to stick in all the numbers that we do know and simplify. And so this implies, sticking in the numbers, this implies that 1 over the square root of F equals minus 2 log base 10 of 0.005054 plus 0.001349 feet per second, feet per second divided by U averaged times square root of F. Okay, and this is one equation here. And so here the units work, everything cancels out because F is unitless, and so we need this, we need all these coefficients here to be unitless. So this works if U averaged is in feet per second. Okay. So now we don't know the friction factor. We don't know the friction factor square root of F, and we don't know U averaged. So we have so far one equation and two variables, and so we're gonna need to solve that. And to get the second relation, we go back to the energy equation. Back to the energy equation. So we have U averaged squared over 2g minus the dryer pressure over rho g, which is just gamma, equals minus the total head loss, equals minus, and I'm just going to stick in what we know about the head loss, F times 20 feet over 0.333 feet, that's L over D, times U averaged squared over 2G, and I'm not going to stick in G yet, plus 6.5 times U averaged squared over 2G. Notice that everything here is divided by the same G, so we can just cancel those out. So those will go away. So there was an advantage to not dividing that by G just yet. And so we can solve this for P dryer. This implies that P dryer over rho equals, and I'm going to move P dryer here to the other side, and I'm going to move this head loss over to this side. Okay, and so we have P dryer equals the average velocity squared over 2 times this parameter here is 60, so we have 60 times F, that takes care of the major losses, plus 6.5 plus the kinetic energy for here, so that's plus another 1. Okay, and so I just factored out from this term, and this term, a U average squared over 2. Okay, and we know that rho equals 0.00221 slugs per cubic foot. Okay. And we found out P dryer, so we just stick in the numbers for that. This implies that 1.04 pound force per foot squared over 0.00221 slug per cubic foot. And I'm going to convert the pound force to slug, so 1 pound force equals slug feet per second squared is equal to the average velocity squared over 2 times 60 times F plus 6.5 plus 1. Okay? And so we punch in the numbers for this, and we wind up with 470 feet squared per second squared equals, oops, sorry about that, U averaged squared over 2. I make that square more squarey. U averaged squared divided by 2 times 60 times F plus 7.5. Okay, and so this equation also works in terms of units if U averaged is in feet per second units. Okay, and so this is equation 2. So just like the previous example problem, we now have 2 equations, 2 variables, and so I will take the first equation for the sake of completeness and just copy that down. Okay, so we have 2 nonlinear equations and 2 variables, u and f. Okay, and so now we solve with Wolfram Alpha. And so I'm going to do that again, show you how to do that. Hopefully I don't have another typo. So again, we use the find root command of the first equation, which is 1 divided by square root of f. Oops, and I forgot to put this in curly brackets because it's a list of equations. Equals minus 2 times log base 10 of 0.004054 plus 0.001349 divided by u divided by u times square root of f, comma, then the second equation we have 470 equals u raised to the 2 divided by 2 times 60 times f plus 7.5. So that's the second equation. Close the curly bracket. Then we have the list of initial guesses, and so I'm going to guess f equals I'm going to guess f of 0.1, and I'm going to guess u of, I don't know, 1 meter per second, and run it. Okay, and it looks like I messed it up again. Oh, and I see my mistake here instantly this time. I forgot to close the log 10. Okay, and so this is, and as always with Wolfram Alpha, check the text under the input, and make sure that the equations that it's solving are the ones that you intended to solve. If not, you probably have a typo somewhere. And then if they're correct, and then check and make sure that the numbers are physical. Because when you're solving nonlinear equations, you can have multiple solutions. So for example, you might wind up with a negative f, or an f of say 10 or 1,000 or something like that, or a negative u, something like that. So just make sure that your solution is physical. Okay? And so we know that u then is 0.0292, or f is 0.0292, and u is equal to 10.08 feet per second. Okay? And then from there we get that f equals 0.0292, and u average, I should say, equals 10.08 feet per second. Okay, and so this looks like the final answer for at least for the average velocity, but we need to check to make sure. So check RED to make sure that the turbulence assumption is correct. Okay, so RED, we already calculated that. That equals 1860 seconds per feet times U averaged, and that's 10.08 feet per second. And that implies that RED equals 18,750, which is greater than 2,300. So the turbulence assumption correct. Okay, and again, if the Reynolds number happened to be less than 2300, that means we need to go back and then use F laminar, 64 over RED. Okay, so now we know then that this is the correct U average, so our assumption of turbulence bears out. So then finally we can compute the volumetric flow rate. Q is equal to area times U averaged equals pi over 4 d squared times U averaged, and that equals pi over 4 times 0.333 feet squared times 10.08 feet per second. And that implies that the volumetric flow rate equals 0.878 cubic feet per second. Okay, and so that's going to be the last example that I do for pipe flow. So I really hope these help. Again, these are just the types of problems you have to do them a few times, and then they become fairly straightforward. About the only thing that's not straightforward about them is sometimes you have to solve nonlinear equations, and a couple of them. But again, that's the way most things are in real life when you get to the real design world, is that you wind up having to solve nonlinear equations or solve nonlinear differential equations, things like that, to be able to analyze your system. Okay, and so that ends it for the pipe flow chapter 8.